32nd lecture. Today's topic is Introduction to Random Signals and Probability. But before we start random signals and probability, we would like to work out a couple of examples on Z transforms as promised last time. Z transforms. The first example that we do is the example 1034 in the text, and I chose this example because it illustrates a certain style of working out problems where you have to recognize the fact that if the excitation is of the form z to the n and you apply this to an LTI system, then the response would be of the form h of z, z to the n. In other words, if you know h of z, then you can calculate the response of the linear time invariant systems to a signal, an x of n of the form z to the n. This happens because z to the n is an eigenfunction for the system and h of z is an eigenvalue. Normally what one would do is from h of z, from the given h of z, one would find out h of n and then convolve with x of n. Alright, we don't have to do that, there is a simplification here, and the problem states like this, that we have an x of n given to an LTI system and the output is y of n, and two conditions are given. It is given first that x of n is minus 2 to the power n. If x of n is minus 2 to the power n, then y of n equals to 0 for all n. Alright. What does this imply? It implies that h of minus 2 is equal to 0. That's it. This is the thing that is to be recognized from this. And the second condition that is given, condition 2 that is given is that if x of n is half to the n u of n, then y of n this leads to y of n equal to delta n plus a 1/4 to the power n u of n, which simply gives you a form for h of z in terms of an unknown constant a, and therefore the question is find a. That's the first part of the question, and the second is that determine y of n if x of n is equal to 1 for all n. Alright, it's a 1 for all n. It's not u of n, it's 1 for all n. Alright. So first condition had given me h of minus 2 equal to 0. Second condition gives me h of z as equal to 1, the z transform of y of n, 1 plus, what is the z transform? A divided by 1 minus 1/4 z inverse, right, divided by x of n is half to the n u n, so it is 1 by 1 minus half z inverse. Now to determine a, obviously what you do is you put, how do you find a? You put h of minus 2 equal to 0. That means you put not z inverse but z equal to minus 2. That must be remembered. It is not z inverse. So z inverse would be excuse me, z inverse would be minus half. You substitute here and then evaluate and then put the result to equal to 0. Then you get a, this is my calculation, a becomes minus 9 by 8. And once you have found out a, well, h of z is then given by 1 plus, a is 9 by 8, so 1 minus 9 by 8, 1 minus 1/4 z inverse, 1 by 1 minus half z inverse. I am not converting this into a rational function. I am not converting this into a simplified form because this is not what has been asked for. Do not waste time on this, alright. You understand what I mean? I have not simplified this because I don't need the simplified form. I can evaluate all that I want right from here. And the other thing is x of n is 1. 1 I can write as 1 to the power n. And therefore, all that I want is y of n shall be simply h of 1 multiplied by 1 to the n. We are not finding h of n, we are not convolving, we are simply obtaining the output as h of 1, and you put z equal to 1 here and simplify. Alright, it will be a pure number and the number comes out in my calculation as 1/4. I often make mistakes, so you must check this. Any question on this? The next problem that I take is a problem which illustrates the application of unilateral Laplace transform in solving linear constant coefficient difference equations. And the equation that I take is yn minus half y of n minus 1 equals to x of n minus half x of n minus 1. X of n is given as u of n, and you require one initial condition because it is a first order difference equation, and y of minus 1 is given as 1. So what we do is we take the unilateral Laplace transform ULT of both sides. Then we get, I am sorry, thank you. Then we get, if capital Y of z denotes the unilateral Laplace transform of small y of n, then you have to be careful here. The z transform of y of n minus 1 is y of minus 1 plus z inverse of capital Y of z. This we had proved last time. This is the difference, that if it is unilateral, you require a y of minus 1. Alright. Then this would be equal to capital X of z. Well, what is capital X of z? If x of n is un, then 1 by 1 minus z inverse minus, yes, half x of n minus 1, half z inverse divided by 1 minus z inverse. Is that okay? Because x of n is given as u of n. Otherwise, we would have required a u of minus 1. What is u of minus 1? It is 0. This point must be understood, that y of n minus 1 we wrote like this, but x of n minus 1 we simply write as z inverse x of z. This is because x of n is specified as u of n. For any other function, for an arbitrary function, we would have required x of minus 1. Alright, we don't require it here because x of n is u of n and u of minus 1 is equal to 0. If you simplify this, then you get y of z as equal to as equal to 1 minus half z inverse divided by 1 minus z inverse. You understand where this comes from. We have a 1 here and minus half z inverse, 1 minus z inverse. So it's just combining these two. And from the left hand side, this term will come to the right hand side. Half, and y of minus 1 is 1, so minus half will go to the right hand side as plus half. And this is what I must include here. That's not quite correct. Y of z shall be multiplied by 1 minus half z inverse. And therefore, y of z is equal to 1 by 1 minus z inverse. Note that there is a pole 0 cancellation here. The numerator 1 minus half z inverse cancels with 1 minus half z inverse. Plus half, the other term is 1 minus half z inverse. Now you invert term by term. Obviously, y of n shall be, for the first term it would be u of n, and for the second term it would be half to the power n plus 1 u of n. Is that clear? Why n plus 1? Because there is an additional half here, and that is the answer. Suppose we had a second order difference equation. Alright. Suppose we had, in addition to y of n y of n minus 1 and y of n, we had also y of n minus 2, then how would you transform y of n minus 2? It would have been, yes, y of minus 2, you can easily show this, plus z inverse y of minus 1 plus capital Y of z. Z to the minus 2, okay, that is correct. Similarly, you can extend it to other delayed functions. That completes my discussion on Z transform. We next consider the new topic, that is random signals and probability. Actually, we are going to discuss during this. How many lectures are you getting? 8 more. This is the 32nd. My aim is for 40. We might get plus minus 1. I don't know. If all politicians are alive, we may get all of them. If one of them dies, then we might have to curtail one. Anyway, what I am going to discuss in these 8 lectures, and in thorough details, without pre-assuming any knowledge on your part, random signals and linear time invariant system response to random signals. So, response of, this will be our topic for the rest of the lectures, response of LTI systems to random signals. Well, I expand on this topic because it is very tempting to write the topic as random signals and systems. Well, so long as the adjective random applies to signals only, there is no problem. But when I write random signals and systems, it appears that systems are also random. No, we cannot work with random systems, all right. Our physical world, we must have systems which are deterministic. We cannot have random systems. But unfortunately, there are signals which are random, and therefore, we have to talk about the response of LTI systems to random signals. Random signals sometimes are wanted or useful, sometimes they are useless. For example, noise. In most of the usual systems, noise, the random signal, is an undesired phenomenon, and that is why in communication, as you will see later, this ratio, signal to noise ratio, is an extremely important parameter. You can also appreciate this if you keep your stereo at a very low volume. At a very low volume, theoretically, if there was no noise, you should be able to hear, decipher. But if you put it sufficiently low and the level of the stereo output is comparable to the noise level, then it does not make sense. All that you hear is noise. Now, incidentally, that we have already introduced what is a random signal. That noise is a random signal. A random signal is one which varies randomly. Okay, that's a simple definition. Now, what is a random variation? And what is a signal? First of all, let's recall what is a signal. This was discussed in the first lecture. What is a signal? A signal, any input to a system. All right, it may not be an input, it may exist by itself, a signal. The output of a signal generator, you may not connect it to any amplifier or any other system, still it is a signal. So, what is a signal? It is a function. It is a function of a variable, at least one. It could be a function of more than one variable. For example, a picture signal. In a picture signal, the amplitude or the intensity of light at that point, and the space coordinates, these are the variables. Space coordinates are the variables. The signal that we have been considering is a function of time. And I also pointed out that time is not a sacred independent variable. There may be other kinds of independent variables. So, for a signal, for a function to be a signal, is there any other characteristic? for can an arbitrary function be considered as a signal? For example, a 12 volt power supply, is that a signal? I have already told you that it is not, isn't it? For a signal, it must vary with an independent variable. A constant quantity is a bore, it is not a signal, it does not carry any information. Similarly, all time varying quantities are not signals. For example, a pure sinusoid cannot carry any information. Well, it has a frequency, it has an amplitude, that is it, and it is predictable at all times to come. Unless we modulate a sinusoidal signal, unless we modulate a sinusoidal waveform, it is not a signal. A pure sinusoid cannot carry any information. So, all functions are not signals, but signals must be functions. They must be dependent functions, dependent on one or more variables, all right. So, what is a random signal then? A random signal is one which cannot be, whose variation with the independent variable cannot be predicted. In other words, the amplitude of a random signal varies arbitrarily and randomly. That is, you cannot predict. For example, if you have a signal like this, a modulated signal, an amplitude modulated signal, it is possible to predict its value at all times to come and all times in the past. We know the specific law of variation with time. On the other hand, noise, for example, at the output of a stereo system, where you cannot predict what will happen, how much noise will be 3 seconds later. It varies randomly, and noise is an excellent example for electronics and communication and computer engineers as an excellent example of random signals. There are other kinds of random signals which we shall come across in due course of time.
How can we call it a function of a variable then?
Because it does vary with time. Well, the amplitude, if you record noise, you can record it. You amplify noise by means of an amplifier. Amplifier itself adds its own noise to what you are amplifying. You can record it, and it varies with time, and therefore it is a signal. It varies with time in an unpredictable manner. You cannot predict, and therefore it is a random signal. Well, so one of the characteristics of a random signal is that it cannot be, its amplitude cannot be predicted. Its instantaneous value cannot be predicted. Well, for a random signal, the instantaneous value is not important either. You know, it's like, since we cannot fight it, we join it or we accept it, all right. We cannot predict it, and therefore we say it's not important. So, we must find alternative ways of characterizing a random signal, and the alternative ways are, for example, average power. We can measure the noise power, all right, the average power. Noise power obviously measured over a certain interval may not be the same as over another interval, all right. So, we say average power during a certain interval, we can always measure, or we can measure its frequency spectrum. Noise can be white or colored. Noise can be white or colored. White noise is one in which whose frequency spectrum extends from minus infinity to plus infinity. That is, it's a constant, all right. That is called white noise. Incidentally, this term we introduce right away. A colored noise is noise, a random signal, whose frequency is, whose spectrum is band limited. In other words, it does not extend from minus infinity to plus infinity, it is limited over a certain band of frequencies. We can have red noise, green noise, and things like that, okay. So, for a random signal, instantaneous values cannot be determined, instantaneous values cannot be predicted, and they are not important either. We consider them as unimportant because we cannot measure it, we cannot characterize a signal in terms of instantaneous value. What we characterize is in terms of average power, frequency spectrum, or even a statistical measure like probability. Probability that its amplitude exceeds a certain value. We can always do that. We can put a line at the value, let's say capital A, and we can measure the probability that the amplitude is greater than A, or maybe amplitude lies within a certain range, let us say A to B. All right. These are the things which are important for a random signal, as opposed to what is not random is, what is the other term? What is the opposite of random? Predictable or you have to be a bit sophisticated, deterministic. Yeah. We don't call engineering drawing nowadays. What do we call? Engineering graphics. Yeah. So, what is opposite of random is deterministic. Okay. Now, there are basically two kinds of models for characterizing random signals. Random signals. Okay. And these models are, one is the probabilistic model, and the other is the statistical model. All right. We have to distinguish between the two. The probabilistic model is not that is a precise model, is a more precise model than statistical model. Probabilistic model is more precise than statistical model, but unfortunately we cannot use probabilistic model, that is only probability, either discrete or continuous, in system analysis. What we do is, from the probabilistic model we go to statistical descriptions of the signal, and these descriptions can be averages, that is averages like mean or variance. We shall introduce these terms one by one, even if you may be slightly familiar with this. Did the mathematics course do some probability?
No, sir. No, sir.
Or you know nothing about probability yet, except for JEE. There was a small section on probability there, isn't it?
Yes.
We forget about that. That was learning under stress, and learning under stress is no learning. All right? One forgets as soon as the exam is over. So we are now trying to not learn, not be able to solve problems. We are trying to learn. We are trying to understand the basic concepts. Okay. Mean, variance, then there are functions, then there are statistical measures like correlation function. We will talk about this. Or we talked about the frequency spectrum. We can talk about, in the probabilistic model, we can talk about spectral density. Have we introduced this term already? Yes, we have. Where? Spectral density. In Parseval's relation, yes. Capital X of omega, magnitude square d omega divided by 2 pi, integral from minus infinity to plus infinity, is the total power in the frequency domain, and capital X of omega was characterized, was this characterized spectral density? Square of it, mod squared was characterized. So, as you will see, for a random signal, it is spectral density is an extremely important parameter to consider, because we can analyze linear systems. If spectral density of the input is given, we can find out the spectral density of the output. It's very easy, and one can, even without knowing anything about random signals, one can find out, one can predict what will be the relation. Obviously, the output spectral density would be the spectral density of the input multiplied by the magnitude of the frequency response function squared. All right. This is a very, very easy, this is a very, very convenient measure, the spectral density, and this is a property of the system, which is a linear time invariant system. All right. So, if you know the spectral density of the input, obviously you can find out the spectral density of the output. This we shall see later. As I said, the statistical model is less precise than the probabilistic model. However, there is no other way. Statistical model has to be used if you are to find out the response of linear time invariant systems to random signals. Then we introduce the concept of probability. Probability Well, that you have that Pankaj has come to the class today is a certain event. Whether Pankaj will come tomorrow or not, well, okay, I have to take the roll list to name a person whose coming tomorrow is uncertain. Now, such an event where the output, well, let's consider like this. Every happening with random signals is called an event. Every happening is called an event, and all such collection of events is called an experiment. We redefine our concepts of experiment. For example, the usual thing that one takes is a tossing of a coin. If you toss it, let's say 20 times, then the outcome of each toss is an event, all right, and this is called an experiment of tossing a coin 20 times. This is an experiment, and every outcome is an event. Now, every outcome, no outcome is deterministic. We don't know what will happen. It can happen in two ways. It can be either a head or a tail, all right. So, if the outcome of a certain experiment is uncertain, then the event is called a random event, all right. I have introduced three terms. One is experiment. Experiment is a collection of events. Another is an event. Event is the outcome of an experiment, of one experiment or one step of the experiment. And we have also introduced, if the outcome of an experiment is uncertain, then we call it a random event. Now we can introduce the concept of probability. Probability philosophically, it is linked with the frequency of occurrence of an event, all right. For example, in the tossing of a coin, there are two possible outcomes, H and T, head and tail, and they can occur with equal probability. In other words, if you toss, there is no reason why, if you toss, let's say 1000 times, there is no reason why heads should occur more frequently than tails, and therefore they occur with equal probability. And with equal probability, where probability is now being used in the qualitative sense, in the quantitative sense, probability of getting a head is approximately half, well, the number of times that a head will occur. If you toss the coin sufficiently large number of times, would be about half. If you toss 500 times, then there is a probability that 250 times you will get a head, and therefore the probability is half, and it is the same as the probability of a tail, all right. Well, I have not yet given a formal definition of probability, but qualitatively the probability of getting a head or the probability of getting a tail is half. That is, if you carry out the experiment capital N number of times, it is probable, it is expected that n by 2 times head will occur and n by 2 times a tail will occur. But probability is not just in terms of discrete events like this, it could also be a continuous event. It is, however, more convenient to talk about probability as a discrete event first, discrete probability, and then go to continuous probability, which is the path that we shall follow. But formally, we now define probability as the number of experiments and the number of times that an event A, now we use a capital P of capital A, that means probability that an event A occurs is number of times that A is likely to occur. We do not actually measure the number of times that it actually occurs, is likely to occur or expected to occur, all right. So, let us call this N A divided by N, NA is the number of times that A is likely to occur, and capital N is the number of experiments performed. Now, the actual number of times NA prime equal to actual number of times that A occurs is not necessarily equal to NA. However, it is known that if N tends to infinity, that is if the number of experiments tends to infinity, if it is very large, then NA prime, well, NA tends to NA prime. Alright. If the sample size is sufficiently large, then the probabilistic measure or the probability is more accurate in terms of the number of times that an event occurs, that an event actually occurs, and that approaches the number of times that an event is likely to occur. We have simplified the concept of probability. Probability can be a very involved phenomenon. For example, suppose an observer is sitting on the time axis at t equal to t0. There is an observer here, all right. I am not good at drawing figures, but somebody is sitting here at time t0, and he freezes, the time frame, and he wants to find out, this is the amplitude, he wants to find out between amplitude A and B, all right, how many time functions start. Let's say t0 is the starting point of time functions. There are many random time functions that start from here, and they can start literally from 0 amplitude to infinite amplitude. He is interested in finding how many time functions start between or in the range A to B. The probability now is not of one event, it is of multiple events, and the probability we will write between, let's say, A amplitude less than A less than B. You understand, this is not head or tail, this is not a binary phenomenon. It is not an outcome of, let's say, 3 or 4 possible outcome, 3 or 4 possible results or events. It is a continuous range from A to B, and he counts, he observes how many functions start from t0, and if this number is denoted by NAB, and the total number of time functions that start at t equal to t0 is capital N, then the probability is simply NAB divided by N. Probability is a number, and obviously probability is to be a positive number. Positive, it cannot be negative, all right. It is a positive number, the lowest value being 0 and the highest value being 1, all right. So, if Pankaj comes every day, then the probability of Pankaj coming to the class is 1. That is, PA is equal to 1 if A is a certain event. That is, we know that it will occur, all right. Winter shall come after summer. So, coming of winter is a certain event, and the probability of winter coming in a year is 1. On the other hand, there are some characters who never appear in the class, who never come to the class, and that is the probability that he comes is 0, all right. If A is an, what is the opposite of impossible event? Impossible event, all right. And the probability of any event shall lie between 0 and 1, all right. As I said, our interest is in continuous probability, but it is more expedient, it is more convenient to introduce probability concepts in terms of discrete probability, and that is why we are following this route. Let us go a little more details into the concept of an event. as I said, if it is tossing of a coin, we will gradually complicate matters. Tossing of a coin, the possible outcomes are head and tail, and the probability of head and the probability of tail is half. Suppose we have a die. A die is a, what is it? It's a cuboid. Isn't that right? It's not a cube. Oh, it's a cube. Okay. It's a cube. And you have marks like 1, 2, 3. There are 6 faces, and therefore when you roll a die, the probability that it will settle with the top face equal to 1 would be 1/6, because there are 6 possible outcomes and one of them has to occur, 1/6, and this is also equal to P of 2 and so on, P of 6, all have equal probabilities. You also notice that if we can state now in general terms that if there are capital N number of experiments and if there are capital M number of outcomes, N experiments, capital M outcomes, well, here there are 6 experiments and there are 6 possible outcomes. Well, N can be greater than M. You can roll the die 20 times, all right. So capital N and M are not related except for the fact that capital M, number of outcomes, and the number of experiments, to be able to make some qualitative descriptions, some qualitative relations between probabilities, N must be greater than or equal to M. Otherwise, all outcomes may not be visible, all right. If there are M possible outcomes, then your number of experiments must be at least M. Suppose the outcome 1 occurs N1 times, outcome 2 occurs N2 times, and so on, and you add all of them. The mth outcome occurs Nm times, then obviously the sum of them must be equal to N. And if you now divide by N both sides, then obviously what you get is probability of the first outcome, probability of the second outcome, and so on, plus probability of the mth outcome. Obviously this must be equal to 1. So all the probabilities, if it is a complete experiment. What is a complete experiment? An experiment which gives a chance to all events appearing. It's a complete experiment. For example, if you roll a die 5 times, then it is not a complete experiment, because all the 6 events, all the 6 outcomes didn't get an opportunity to show themselves. All right. So in a complete experiment where capital N is greater than or equal to M, the probabilities must add up to unity. All right. This is one of the things. For example, in a head or a tail, you can see that PH plus PT is equal to 1. Similarly, in the die rolling, P1 plus etc. plus P6 is equal to 1. Let's consider more complicated events. These are simple events, only one simple outcome. Suppose two of you, Kaustubh and Asim, they are tossing 2 coins simultaneously. Well, the outcomes can be 4 types. Both of you can get head, both of you can get tail, one can get a head, the other a tail, and one can get a tail and the other a head. Obviously, these outcomes are indistinguishable, one head, one tail, unless you mark Asim got a tail and Kaustubh got something else. But here it is a joint experiment, all right. So it is a joint probability. It is a more complicated event, 2 experiments being performed simultaneously, and you see that PHH, it's no longer half, it is 1 by 4. Similarly, this is also equal to PTT, but PTH is half. All right. This is a more complicated event. One could, for example, as an example, of more complicated event, one could take the die rolling experiment. That is also an experiment. One could find out the probability that the number shown on the face, on the upper face, is greater than 3. This is a more complicated event, because 4, 5 and 6, these are the only numbers which are included, and they together form one event. Therefore, there are two possible, how many possible events? 3 possible events. What are these possible events? Number greater than 3 is one event, alright, less than 3 is another event. So, there are 2 possible events.
Less than equal to.
Equal to 3, okay. So, that is another event. Less than equal to 3 is one event, and greater than 3 is another event. So, more complicated event. Or you may get, you may be interested in finding the probability that the number is even. The number shown on the upper face is even. In each case, you can calculate the probabilities. We shall not do this right away, but we will we'll take an example, a fairly complicated example of calculation of discrete probabilities. We'll take a box with 100 balls, 100 balls, and these 100 balls can be of various sizes, but they are distinguished by their colors. And the color distribution, I'm just cooked a hypothetical example. Let the color distribution be like this: red 10 balls, black 20, white 40 and green 30. Someone reaches into the box and picks up a ball. How many possible events can occur? This is the only description. 4. Well, it has to be one of these colors, alright. So, there are 4 outcomes, capital M equal to 4. A complete experiment would be performed if 4 times someone draws. Actually, in probabilistic measures leading to statistical models, the number of experiments must be much larger than the number of outcomes. To be able to give a statistical description, capital N must be much larger than capital M. Now, you can calculate the probability of a red ball. Obviously, it is 10 out of 100, and therefore it is 0.1. Probability of a black ball being picked up is 0.2. Probability of a white ball is 0.4, and the probability of a green ball is 0.3. And you can see that all of them are positive, less than 1, and the sum of them is equal to 1. Sigma is equal to 1. Now, let us complicate matters and and talk of joint probability now. That is, we now distinguish between the balls in terms of weights. Let us say the sizes are different, and we make it into the form of a matrix, weight in this direction and color in this direction. We have red, black, white, green and total, and weight, let us say 1 gram, 2 grams and 3 grams. Let us have 3 different kinds of weights. And the distribution arbitrarily I have chosen 5, 5, 0. So, the total, again total is 10 red balls we have taken, black 10, 5, 5, the total is 20, white 25 of 1 gram, 0, 15, and this is 40, green 0, 10, 20 and 30. The totals would be 40, 20 and 40. So, the total on this side or this side has to be 100, total is 100. Okay. Now, we want to know what is the probability of picking up, let us say, a green ball which has a weight of 3 grams. obviously there are two characters now given, right, and therefore this is a joint probability. We can talk of the probability of picking up a red ball, that we have already seen. Picking up a red ball, the probability is 0.1, 10 divided by 100. But now we are attaching another character. Let us say the probability of picking up a green ball is 0.3, but probability of picking up a green ball which has a weight of 3 grams, well, how many are there? How many are there? 20. 20 out of 100, and therefore the probability of picking up a green ball having a weight of 3 grams is 0.2. Well, this is called a joint probability. Why joint? Because two characters are attached to the event. The event is not just color, the outcome is not just color, but also the weight. How many such joint probabilities will exist in this experiment? Total 12. 12 joint probabilities. Okay. In general, joint probability is defined as PAB, which means that it is the event is a combination of happening of A as well as B. Both must occur. All right. Then it will be called an event, and the probability is denoted by P A comma B. Now, how do we calculate this probability of? How do we calculate the joint probability? Well, if a matrix like this is given, obviously we can calculate. In general, the joint probability is calculated in terms of two quantities. One is called the conditional probability, and the other is called marginal probability. Let us introduce these terms. Conditional probability is denoted by, the notation is something like this, PA stroke B, which means that the probability of the event A given that B has occurred. All right. This is called conditional probability. The condition is that B event has occurred. For example, in P we can have PG3, that is a 3-gram ball has been picked up. What is the probability that it is green? You understand what I mean? Conditional probability. One event has occurred. This event 3 gram has occurred. That means you have picked up a ball from the box which is 3 gram weight. Then you ask the question, what is the probability that it is green? Can you tell me what this shall be in this context? 0.5. Okay, why is it 0.5? Because 3 gram ball has been picked, and 3 gram ball there are 40 of them, and you ask the question, what is the probability that it is green? Green only 20 of them, and therefore 20 divided by 40, that is half, 0.5. And these ordinary probabilities, that is probability of a green ball being picked up, or probability of a 3 gram ball being picked up, that is a single characteristic event, the probability of a single characteristic event, these are known as marginal probabilities. All right. We have already calculated the marginal probabilities of the colors PR, PB, PW, PG. We can calculate the marginal probabilities of weights also. For example, what would be the marginal probability of 1 gram? Obviously, it would be 0.4. Similarly, marginal probability of 2 grams will be 0.2, and marginal probability of 3 grams will also be 0.4. These are marginal probabilities. Marginal probabilities imply that there exists more than one character to each event, but we are isolating events as belonging to a single character. All right. Do I sound abstract, or is the concept clear? If not, then I will go through this again. Is the concept clear? We shall show, not show, we shall demonstrate next time that the probability, joint probability of two characters A and B is given by the product of, this is a famous theorem in probability, Bayes theorem. Okay, you know the name also. It is the conditional probability of event A after B has occurred multiplied by the marginal probability of B, or it is the same as P B by A times P A. Does everybody know about this Bayes theorem?
Yes, sir.
All right. Pardon me? Under stress. Well, you can verify from this table, from the matrix that I have given, that this is true. It is only a verification. I am not saying it is a proof. We are not proving this. We are not proving this. For example, you see PG3, which you found as 0.2, is PG with 3 gram has occurred multiplied by P3. What was this? 0.5 and 0.4. This is equal to 0.2. Either way, it is correct. I conclude this lecture by asking you a question, that is, under what condition is this joint probability equal to PA, that is the product of marginal probabilities? A and B must be independent events. Okay, we will close here, we will continue next time.